Let's talk about transformations as an introduction to talking about isomorphisms, which is the subject of section 4.2. Transformations are functions. They send elements from a vector space V to another vector space W. Sometimes V and W might be the same, like functions sending numbers to numbers, but in the general case, they are not. I'm going to represent the vector space V with a box with straight edges and the vector space W as a box with squiggly edges to show that it might be a different kind of vector space. Moreover, these two boxes have different heights. The height represents the dimension of V and the dimension of W. So here we see that the dimension of W is greater than the dimension of V. The width of these two boxes is irrelevant. Now, box V is full of elements, and all these elements, when they go through the transformation, go into W. But they may not go everywhere into W. They go to a certain subspace of W, and that subspace is called the image of T. The image of T has a certain dimension. Some elements of V are special, and they are special because all of them collapse and they all go to the one element 0 in W. That special area in V is called the kernel of V, and it also has a dimension. It's the dimension of the kernel. Now on this image you can see that the dimension of the kernel of T plus the dimension of the image of T is equal to the dimension of V. The dimension of W is really unrelated. It could be greater, even greater, or a little smaller. All the area below the image of T is an area that the transformation doesn't reach. These are elements of W that you cannot reach with T. So this is the general situation, the most complex case, if you want, of what transformations are. Now, isomorphisms are a special case. They're actually a case we like a lot. It's an easier case. There's two things that are special with isomorphisms. First of all, it is a transformation from V to W. V is still the same box, but to be an isomorphism, W needs to have the same dimension as V. That's the first thing. So dim V equals dim W. Secondly, all the elements of V, when they are transformed, they fill up all of W. The image of V is equal to W. That's the second thing that is needed. There's another way to think about that, and it's to think about the kernel. The kernel is made of all the elements of V that go to 0 under the transformation. And in the case of an isomorphism, there's only one element in the kernel, and it's the element 0. So the element 0 in V goes to the element 0 in W. Therefore, the dimension of the kernel is 0. What's great about isomorphisms? Well, the main thing is that when you have an isomorphism, you can go backwards. You can go from W to V. That means you can find the inverse of transformation T. In the general case earlier, you couldn't find the inverse of that transformation. So that's it.